limited series production. Then this is the one case study we made it for our DRDL application for basically torradile air bottle application. We did the entire thing. We modified our part based on the suiting to our additive manufacturing. See, challenges, accelerated qualification. Now qualification things are why current qualification certification methods are costly and time. It takes lot of huge time and resources. Why? You see that next slide. This is a slide. In this one, other side that bigger portion components are there. So almost this is a 600 by 600 Nikon, almost 1.2 meter machine. Nikon. This machine, if I have to certify for production, okay, they have to make 1800 as per our NASA other standard. They have to make 1800 samples. Full build volume they have to produce 1800 samples. That qualification takes 18 months. But none of the industry can afford for it unless you have a quantity. Similarly, entire build space, you have to make that too. You have to repeat anything. You have to repeat for at least 3 lot of powder variation. Almost to capture entire build volume, you have to map it with the samples. That takes time consuming. Minimum they are taking that this kind of bigger industrial grade parts. Almost people are taking 1 year. Suppose we are building some 300, 400 test coupons, testing and machining, everything takes years together. That is the one major issue is their qualification. How to address this? The people are coming up with another solution. See, can we qualify the similar part with the maximum efficiency? How? Part family concept. Suppose I will group that similar parts with the similar features. If the similar features, one part with similar feature, it's get qualified. The other part also can follow up the same qualification methodology. That way, so that your qualification time reduces. One machine is qualified for similar part with similar features can be printed on the same machine. See, same material, same post-processing content. That way, similar geometry and section thickness. Part family, there are different things are the certification part family, feature part family, qualification part family, and sustain ASTM part family, different. Now, let us say ASTM, how classifies the part family. You see this, they proportional to criticality. See, if the criticality is classification A, B, C, D, they are classifying consequence of failure is high, medium, low. This is as per ASTM standard, the standard is already published. Accordingly, they are classifying that. Based on the classification, the qualification methodology will differ. The negligible that will have a less qualification requirement. Critical things will have a higher qualification requirement. That way. Another thing is digital data management is another critical thing. Actually, this in afternoon they asked the question that how to manage the digital thing. This our Semilac is putting a lot of effort on this. They are going to put one national server. Almost they are investing almost some 300 to 400 crores. Almost all industries can put their data, upload the data, because any additive manufacturing thing, whatever institute monitoring thing, our smaller build, each build I will generate almost 20 to 30 GB data. Storing the data is very difficult. They are building national level one server, they are planning that. This is already in the pipeline. That will come up in due course of time. See, model based, then another thing is ICMA based, ICMA and data science based qualification framework. Before building the part itself, they will entire thing, they will run on it in the digital world. Then any model variation, anything to be modified, they will see that once things are okay in model level, they will do actual printing. But it is a futuristic approach. It is not a correct approach, it is a futuristic approach. Basically, today we are at single part qualification. Industries are going towards a similar part complexity, part family concept. In future, we have to go with long-term machine agnostic and physics-based models. This is what. Thank you.
Thank you, Mr. Gopi, for very succinctly bringing out what are the challenges we face during the qualification and certification of components which are produced through additive manufacturing, and what are the different advantages additive manufacturing offers us over the conventional processes of manufacturing. So we'll have question and answer sessions after the second speaker finishes his presentation. So now over to Commander Gadke. He's going to speak on the subject of additive manufacturing for naval aviation.
Good afternoon, everyone. In the next 10 minutes, I shall cover the requirement, present status, and advancements made in additive manufacturing in the field of aviation and aerospace. The scope of the presentation is as shown. At the outset, I shall give the overview of indigenization organization of naval aviation, which coordinates the design and development of aircraft spares to achieve the objectives of self-reliance and Atmanirbharta. Design, development, and manufacturing of aviation components through additive manufacturing will aid efforts of indigenous development. Directorate of Air Projects and Plans is a nodal directorate at Naval Headquarters which coordinates the indigenization of aircraft spares and development of aircraft LRUs and systems under various GOI schemes. Headquarters Naval Aviation, HQNA, is a class authority which coordinates with all in-house indigenization committees and NASDO for preparation and monitoring of indigenization tasks on a periodic basis. IICs at Goa and Kochi undertake indigenization of aircraft spares of Eastern and Western origin aircraft respectively in association with industry partners. And NASDO Goa coordinates the induction of COTS items required for enhancing the productivity and efficiency of maintenance units. Now coming to the latest manufacturing technology which is growing rapidly in the field of aviation and aerospace due to its numerous advantages over a conventional manufacturing method. Details have been covered by the speakers in pre-lunch session. Therefore, I shall recap only the basics in short. Additive manufacturing, commonly known as 3D printing, which is a transformative manufacturing technology involving layer-by-layer manufacturing directly from digital design data. Unlike subtractive manufacturing, which removes material from a billet, additive manufacturing builds parts additively, enabling near-net shape production and significantly reducing the material wastage. Typical additive manufacturing process includes powder bed fusion, directed energy deposition, binder jetting, and material extrusion. Layer thickness ranges between 20 to 100 microns in high-precision aerospace applications. Additive manufacturing allows for complex geometries, lighter structures, and faster production, which is difficult to achieve in traditional methods. Now I shall highlight the need to adopt the additive manufacturing on a larger scale and the vital benefit it offers offered by additive manufacturing technology. Indian Navy operates different aircraft designed and developed by foreign OEMs of Eastern and Western origin and also produced by Hindustan Aeronautics Limited. For aircraft produced by foreign OEM, there is always a dependency on foreign OEM for supply of critical aircraft spares. Naval aircraft operate in a corrosive marine environment and are also subjected to high stress and temperatures. Also, traditional manufacturing processes have limitations in manufacturing of critical and complex components. Additive manufacturing overcomes majority of these issues and offer various benefits like part consolidation, which involves combining multiple components, reduction in time, cost, and weight of the component, topology optimization, and enhancement in fuel efficiency. Globally, additive manufacturing has gained significant traction in aviation and aerospace industries. I shall cover the details of global and in-country leaders and important applications in the field of aviation in subsequent slide. Leading global companies such as Airbus, Boeing, General Electric, and Lockheed Martin have successfully integrated additive manufacturing into their production process. Boeing and Airbus use over 25,000 AM parts in operational aircraft. In India, HL has installed metal additive manufacturing systems capable of processing titanium alloys and Inconel. ISRO has successfully deployed additive manufacturing for cryogenic engine injectors, reducing the production time by 60% and cost by approximately 30%. Some of the prominent aviation component applications are fuel nozzles, combustion chambers, cabin frames, air ducts, and UAV frames. The advancement in artificial intelligence are greatly enhancing the efficiency of additive manufacturing. I shall cover the positive impact of AI and latest trends in additive manufacturing in subsequent slides. Airbus used AI-based generative design for designing a cabin partition. AI-assisted design resulted in extremely light but strong partition meeting the strength, parameters, and reduction in weight by approximately 45%. Second example is usage of AI optimization used for redesign of fuel nozzle of jet engines. The nozzles made from 20 different parts were printed as a single optimized component which was lighter, stronger, and 5 times durable. A digital twin is a virtual replica of a physical object that could be any minor component or a major item like engine. A digital twin on ground simulates conditions like high speed, intense heat, and stresses on the item, and testing can be done on digital twin prior printing of the item. The important example is digital twin technology used by General Electric for its jet engines. Each engine digital twin monitors the performance, and if component shows any signs of stress, item is redesigned and reprinted with improved version. Digital twin combined with additive manufacturing ensures development of efficient, reliable components sustaining the demanding operating conditions. A wide range of materials are used in additive manufacturing depending on the application and required properties. In aviation and aerospace applications, metal additive manufacturing is primarily used. Commonly used metals include titanium alloys, aluminum alloys, stainless steel, and nickel-based superalloys such as Inconel. Advanced materials such as cobalt chromium alloys and maraging steel are used for specialized applications requiring high toughness